really happy to introduce Guido, who's this is his second internship here, so you probably are quite familiar with him already. He's been working on almost everything in F-star, but he's going to talk about the metaprogramming framework in F-star and both its design and some of its applications.
Thanks. Thanks everyone for coming. So yeah, I'm going to speak about what we did for the past wild 3 months. We've been all over the place. So yeah, really excited to tell you about it and hear your comments if you want. So you probably all know F-star. It's you all work here, or so in very briefly. I really don't want to spend a lot of time. So in one slide, I can say that it's a dependently typed, effectful functional programming language. It's designed for verification, and not only that, but it's designed for efficient verification. So to not spend a lot of time trying to verify your programs, but leverage automation as much as possible. So it's in the ML family. It's a higher order language, polymorphic, strict, safe, type inferred, all of the usual things you would expect.
Strict,
yeah.
What does it mean?
Call by value.
Sorry?
Call by value, not lazy. The specs you can write over both values and effectful computations are very expressive. I would almost say arbitrarily expressive. Even over the effectful terms of the language, which of course do not form part of the logic, but you can still specify them properly. There's a proof-irrelevant logic based mostly on refinements and a WP calculus, where the proofs are not really materialized in the source code or in the language itself. It's on a logical level, and we'll speak a bit about that as well. And that's one of the big factors that allows us to use an SMT solver to discharge most of the proofs. We usually use C3. I think we had experiments on using other solvers, but we mostly use C3 in practice. And now a quick taste of F-star, just to get going. Here's like a very small two F-star functions working over the state effect. They're not annotated. Most of the things can be inferred. So this is an increment function, takes a reference to an integer, and it adds 1 to it. Amazing. Then there's this f function that allocates a new reference with a starting value of 1, calls incur, then reads the reference, and there's an assertion. This is a static check that the value v must be equal to 2. And this program verifies, and this is only due to the WP calculus and the logical context that F-star handles and has at all points, because nothing in the types or anything visible here will tell you that v must be equal to 2. It comes from the spec of incur, which is inferred, and so it has basically a post condition saying that it increments a thing by 1, and if you call incur, you get to assume it here and all that. So the first thing you should take from different to, say, Coq or other languages is that you do not have your hands on the entire program context and everything you need to do to show that this assertion holds. There's just no, without going into these things that are not immediately at hand, you just cannot show it. And so most of the times we write these programs, write these assertions, and annotate these specs with whatever we want, and that gets us through like more than half the way there. We verify things pretty fast using the SMT solver. But at some point, the solver must fail. Solvers are inherently incomplete. Of course, it's an undecidable problem, so at some point, they're bound to fail. But beyond that, there's things that don't look so complicated, but still make the solver go nuts. So let's take this small example of this is a lemma in F-star's standard library about modular arithmetic, or just the modular division, saying that a over p is the same that if I take the remainder and then divide by p, then it's the same, because this doesn't, it's less than 1p, whatever. And you would expect to write this and just say, okay, SMT solver, go and find it, but it won't find it. There's just no way for this to find it, or at least not reliably. And what we usually did before we had a tactics language is find a bunch of lemmas that basically break down this into the smallest set of facts that we know are true and call them all, assert them all one by one, and basically guide the SMT solver into finding the proof. So in this case, the programmer, which was pretty heroic to prove this lemma, made use of 3 other lemmas already proven, and then added these assertions to guide the SMT solver in the proof. And then this worked reliably, I guess. So
Real example?
this is a real example, yes.
Okay.
Yeah, and this is like not one of the biggest, to be honest.
Heroic, but this is, I
We
mean,
know
in
who to-
comparison to some of the other proofs.
Yeah, I think I imagine it was J.K. and
Probably.
Yeah, I'm checking the
I'm-
doc.
yeah, yeah.
It is JK.
So
Yeah.
the heroic is for J.K. Maybe not for this lemma, but
Yeah,
I mean he.
JK is, the heroism of JK is extends beyond these things. It's
Yeah, yeah.
very tedious.
Yes.
Yeah.
I'm gonna take a little picture and send it to him.
Sure. So some proofs we want to do are just out of the solver scope. We're not going to be able to get them efficiently the solver will not find them efficiently or reliably, and we cannot do them efficiently as programmers or as verifiers by finding all these lemmas, writing all these assertions. It takes a long time. So I guess at this point it was the main motivation for a tactics engine, which we started last year actually. So this is partly repeating the talk that I gave last year, I guess. So we want a way to take this thing that we need to prove and tweak it before sending it to the SMT solver, and not by modifying the program's source code and manually, possibly somehow do it automatically. And by the shape of these things, write a metaprogram that will attempt to break down the proof in some well-defined way. Before sending them to the SMT. We don't want to get rid of the SMT. The SMT works. It's fast. It's when in the domains where it works really well. So we do not want to get rid of it. That was never a goal. So this is maybe a digression, I guess. It's a bit badly placed, but what we want is a way to have tactics or metaprograms. I'm mostly going to use them as synonyms for now. To modify the proof state. And what I'm calling the proof state is the set of things you need to prove at a given point in time. So in this lemma, for instance, we start with a single goal that it's in some context, in some context of like typing and assumptions, prove this thing. And metaprograms in general are things that perform correct transformations of the proof state. We'll take one proof state and give you another one that whose validity implies the previous one. So if we start with they're basically a set of goals. If we start with a single goal, such as this one, in context gamma 0, find me something of type T0. This could be a proof, right? I'm sketching a bit over, but trying to prove a lemma is more or less isomorphic to finding a term of a given type related to the lemma. So I'm just going to deal with, assume that all of the goals are kind of typing goals. Then you need to find the term of a given type. The proof state is a set of these goals, and what we're trying to do is apply steps that break them down in whatever way we see fit as verifiers or as metaprogrammers. And the usual thing we do, or actually, sorry, the only thing we do is break them down in ways that are, so we break this goal into any amount n of other goals in possibly different contexts and different types and new existential variables, such that if we find the solution to all of these, then we get a solution for this one. And that solution is also well defined by some function of the solutions above. This is very LCF style if you're familiar with the LCF process system. Right, and by designing these primitives to be valid what I'm calling the primitive is basically this rule R, this judgment R, that allows you to move from this to this and instantiate this existential variable. If all of them, we design them faithfully by following F***'s typing judgment, its formal definition, then all of this ought to be safe because it simply follows the definition of the language. This is an example. So these goals are, this is an example of the actual tool running and showing you a goal that we need to prove this huge equality of things and displaying whatever is in the logical context. Right, so That's all well. We want to transform this proof state into other things and do it in somehow safely. How do we actually do it? How do we write a metaprogram? We certainly cannot give the user access to, here's the proof state, do whatever you want with it, and then return back a new one, right? You could just discard goals that you need to show or transform them or whatever. So the way we embed this into F-star is we design a new effect. So F-star has many effects in the language. It models state, exceptions. You can create new ones. And what we do is create a new one for metaprogramming in particular. And it is basically going to be an effect of stateful computations that also raise exceptions, but that's not particularly interesting at this point, over the proof state. And the proof state is kept abstract from user programs. You cannot simply, its representation is abstract, and also metaprograms are not allowed to just set the proof state to some arbitrary thing. They can only modify them via some assumed primitives. And besides these assumed primitives, this effect that we designed for metaprogramming is completely standard. It's absolutely, it's using this feature for effect extension in F-star, where you define a monad and you get a new effect. And which means you get a WP calculus, you get a way to specify them, you get a way to run them and extract them and all that. All of that is reusing previously existing things. So there's the amount of work is really, really minimized. So this is the actual definition. It's a bit clean for the slide, but not very. It's defining a monad proof state into result, which is success or failed. It's basically a state monad and exceptions. Return and bind, and then say new effect, tag has this representation, this return, and this bind, and then boom, we get a new effect tag into the language with this representation. Once we do that, then we can write metaprograms exactly as any other kind of F-star program. So this is an example of, say, some random tactic that this is my tag applied to unit. It returns a unit, but it has the effect tag, and it does an implies intro, which if your goal is an implication, it's going to introduce an hypothesis, and you get it here, you rewrite it, apply some lemma, and you basically write programs as you would in any other effect. Yeah?
At the high level, can you remind me what the difference between a tactic and a lemma?
Yes, a lemma is a term of F-star that has, let's say, just a precondition and a postcondition. It asserts that some value is true. But tactics, I'm calling these computations that transform the proof state. And in particular, tactics can apply lemmas.
A lemma is a fact. Whereas a tactic is manipulating proof state.
Right. It's an algorithm for manipulating.
Yes.
Manipulating and applying lemmas.
Yeah, exactly.
And more things, but yes, in particular, yes.
Yeah.
So how is it referring to the proof state?
It's implicit throughout the computation, the same way as
I see.
in
So-
your...
But it's always implicit? I guess I don't understand.
Yes, in a way it's implicit in the same way as if I had here alloc 1 and then R set to, like in the first program I showed,
Yeah.
there the heap, the actual full state is also implicit.
Yeah, okay.
And the actions of allocating, reading, and writing are the things that modify it. Or if you write in a state monad in Haskell, it's also, and you're only using get and put, the thing is also implicit, right?
Okay.
In a way, it's similar to that.
So if I think of stage computation, tactics as you think of stage like a stage compiler, a stage can manipulate the AST and transform it, and so this is manipulating the proof state. But in the case of like the AST, you actually have the AST explicit. But here you're saying all the proof state is implicit essentially.
He's going to show you the AST as well. Like
Oh,
you also
okay.
get AST.
Okay. So there's more. Okay, cool.
I'm confused. I didn't
It's
follow
so
the
abstract,
eights.
it's just hard for
Okay.
me to see it.
In your metaprograms, do you allow non-determinism?
No, we don't.
So there's no backtracking?
So
there's no-
there is backtracking. You can fail and backtrack, but no real non-determinism.
If you want to backtrack, you have explicitly, say, an ordering in which basically more like prologue. You have an ordering.
In
Tactics deterministically predict the order in which the error is going to be tried and fail, etc.
Yes,
When
yes,
you're
yes.
backtracking,
In
you
a-
have to
yeah.
write code to explicitly simulate backtracking.
Yes, it's quite it's quite
Which
easy.
can be heavy.
I think it's kind of easy given so there's a combinator that will attempt a tactic, and if it fails, it will reset the state.
Okay.
Because in particular, that also has some primitive support to make it faster, because the proof state includes some compiler internals. I'm going to show you an example of a backtracking tactic in a while, actually.
Actually, just also maybe to answer
Yeah.
a little bit of a suggestion for Ben. This tick my lem, you see that there? That's a piece of syntax. It's quoting
okay.
the syntax.
Oh, that's
of
what you
that.
meant. Okay, yes.
Okay, but where did that come from?
That this is
It's
like
in
a
context.
quick
There's
example.
some-
I
term
see.
in
I
the
see. So it has
environment-
to be somewhere. Okay, but
There's-
it's implicit.
Yeah,
Yeah.
there's,
Okay.
there's a name in your program called mylem, and you
Okay.
can quote it and get a
Okay.
syntactic handle to that.
So it's like the actual things you can refer to are actually like global variables or global values you can refer to. Right? Okay.
You can also, also the local ones.
Yeah. Yeah. Okay.
Yeah.
Right. Yeah, I wasn't going to say a lot, so please ask if you're confused about it. But I wasn't going to say a lot about how we handle syntax, and the type of this thing is term into tag unit, so it takes a term. You can build terms independently of if the access is lemmas or not. But I wasn't going to do a bunch of that.
So this is why you're in the exception too, right? Because my lem may not be there.
Yes.
Or you miss-
Yes, this quote actually would succeed, but the apply lemma would then fail in that case. And apply lemma might fail for a million other reasons.
Not a quote. Oh, right. Once you try finding it, then it fails.
Exactly, yes.
Is
Yes.
that the only reason for exception?
No, a lot of things can fail. Apply lemma could fail because the lemma doesn't apply to your goal. You could just raise an error because you want to, or
Yeah.
So
if
when
you
you
just-
write this kind of technique, you have to be very careful. But it makes sense, but you know, right?
Well, so the exception also, is important for doing the kind of thing that Patrice was talking about. Like, if you want to try to process the proof state in a particular way, you make some progress and you see, oh, this is a dead end. I'm not going to finish the proof from here. So you raise an exception, backtrack, and try another path.
Right. Yep. Okay. What I was trying to show with this one anyway was that given this monadic definition that's under the hood, we still can write like direct style syntax for metaprograms, which actually was not easy. Like this time last year, this was not possible. Also, you can write higher order combinators for your metaprograms or whatever. This new effect is really just the same as any other effect. This is the classical repeat tactic combinator that just attempts some tactic indefinitely until it fails and returns a list of results. Right? This is just as simple as this.
Can I have one more question? Can you say one more time why, or maybe, so it's always safe to do these proof manipulations because you give me a trusted set of primitives, right? That's the only way for me to create tech kind of things.
Yes.
Yes. But you have to trust your primitives to manipulate the proof state.
Yes, the primitives are part of the TCB. That's correct.
Okay,
Yes.
thanks.
Given how we call the SMT solver and the proofs are not materialized in many places, it's kind of hard to see how to get certificates and check them and all that, as other tools would do. Anyway, having an effect, we can write higher order combinators. We can inspect the goals and types of terms. This is a more complicated example, so FSTAR has many ways to prove a lemma or to prove a fact. You can use the lemma syntax, or you can just write a function that returns a proof or returns a squashed proof, or many of those kinds of things. And here's like a kind of a utility function that it's like apply lemma, but checks the type of the thing it was fed, checks the type of the thing in the goal, and sees how it can make it fit. And if it's a lemma, then it tries to do something. If the lemma is actually implication, then it's going to try to introduce implication and all that by using all the actions. But then all the rest, like matching, all this, this is just FSTAR.
Just to emphasize something, there's some. So on the third line or the fourth line, you see TC of T, like that's an FSTAR program calling back into the FSTAR type checker.
Right. TC is a primitive of the tag effect, and it's actually wired to call into the type checker.
So it takes the term to, its type.
To its
If it
type.
succeeds.
Yes.
Like,
Okay.
Could also fail. This one could also fail, right?
Right.
You might give it crap.
Okay.
I don't mind if you interrupt, but so yes, there was just an example. So once we kind of had this this piece of the thing working, we can write metaprograms and call into the primitives that are going to manipulate the proof state and all that. How do we actually use them on particular assertions, right? And it's quite simple by following the previous style where we have some piece of code and some assertion in the way, some assertion in the middle, and this was going to be, like previously, this was going to be simply added to the huge verification condition that we're computing for this function and be sent to the SMT pretty much as is. Now we have syntax to slap the tactic in here. This is a thing of type tac unit or tac whatever. And here we're calling some, these are, trfl is a primitive, this compute is some normalization call, and canon is a canonization tactic that we wrote for, say if these things are arithmetic expressions, then it will like try to get them into a normal form before sending them to the SMT. Or actually this would succeed, but anyway. So the thing is that we can, inside a large program, we will have many particular assertions. We can decorate each of them with some particular tactic and run them as we wish. In this case, it doesn't look like much, but this is an actual lemma from a proof of Poly 1305, the scripted primitive, and it's...
Was it written by JK too?
I don't know, actually.
I don't remember if it's a JK one or not.
This is a Chris one, I think.
Oh, okay.
Right,
They're
which I
both
think
equal.
this one, I think this version never worked, actually. This will never, or maybe like one every 100 runs if you vary the random seed, get through the SMT solver.
Maybe the moon phase too.
So yeah, it's a lemma about modular arithmetic, and it's the only fact that's really needed. It's this additional lemma for this basically says that a plus n b modulo b is you ignore the nb or something like this, and then assert this equality. And actually, this is quite easy by just shuffling factors and like canceling and all that. But it's just impossible that the SMT solver will see it in one go. So we now have a way to actually normalize all that. We have a canonicalization tactic. I should stop saying canonization. Generic overall semi-rings. We call it here for the semi-ring of integers because we're dealing with integers. And before dispatching this thing to the SMT, we'll actually normalize them and get rid of all the need for nonlinear arithmetic, which is like the things that the SMT solvers are bad at. And the tactic could do more and could actually get rid of a bunch more of subterms and normalize them more. But we don't have to. We just stop there and send it to the SMT once we know it's good enough, and the thing will just prove it. So by having meta star, which we use here for not only for automation but actually for having more fine-grained control over the things we try and improve or send into the SMT solver. Like this thing, I think, will never, or once in a million years, go through the solver, and this consistently goes through and is faster in all aspects, even if you count the time that the tactic takes and then the SMT solver takes. Yeah.
Is it the use of modular arithmetic that makes it so slow?
Yes.
So if the nonlinear solver at the Z3 was better, would that eliminate the need for a tactic?
I guess, but it's like widely known to be a problem. Not in C3, like usually it's.
Yeah, okay.
So it turns undecidable when I think the linear fragment is decidable. So and apparently also has sufficient algorithms to solve them.
It's known when you do a proof in F star that as soon as you have a fact related to modulo multiplication, you better know how you intend to prove it and call the lemmas yourself, because otherwise there's a proof that's going to break in a week.
Okay.
Or something like we had that.
Yeah, even if you don't have modulo, just in a large context, proving seemingly simple things like, associativity, commutativity of star, of multiplication and plus, like.
Yeah, okay, wow,
So,
okay.
Yeah. Right. So this was a bit from the proving side of things. We're trying to get these assertions to go through more easily. But once we had all this and a way to like poke with F-star's typing judgment and all that, we can actually use it as well to generate terms and new pieces of code, right? So we have this syntax, the underscore by, and there's also synth, the keyword synth that basically does the same thing. So treat them as synonyms. Where we can, when we have an underscore by, the meta F-star is going to run this metaprogram with this original goal, and the metaprogram can do anything to try and solve it. And for instance, this is a really roundabout way of defining one. It's just you get a whole, you get a new goal, and then you apply the primitive exact with a quotation of one that will type check one and see that it fits and get it there. And this one, you apply the addition function, then you get two more goals, and then use exact one, exact two, and this actually generates syntax for 1 plus 2, not 3. It actually gets a syntax for 1 plus 2. And with this automated, like extending this and just repeating the same steps, you can do arbitrarily complex things. One pretty arbitrarily complex thing is what Tahina developed not long ago, which is a set of, it's a library for generating verified parser and generator pairs. So you give it an enum type. So take this one, just for constructors, and having the library in scope with all the tactics defined. This one, this invocation generates a specification for what a parser and generator for this enum must be, and this one actually generates the implementation of the parser, a low-level implementation that meets the spec via this dependency here. This is a carefully defined type. And this is all automatic and actually makes use of, it's very careful of, so in one of these two, I don't know in which one, you need to prove that two functions are inverses, and that's the first one. And that's a proof that's very hard. If you just send it to C3, it's going to take a long time. It's hard to do. So by having control of the way these terms are type checked and the way we construct them, we can actually get that thing as it pops up and just normalize it, because doing enough normalization, you can just prove that it holds, that the two functions are inverses. Which you would not get if you would just like generate the syntax for all this crap and put it here. If you were to have like some external preprocessor that would just generate syntax and slaps it here, you would not have that liberty, because you would get F-star to type check and it will do its default thing and possibly not be what you want. Beyond generating pieces of terms, in some places we can actually generate top-level definitions by large amounts. Like here I'm generating only one, but we can easily do there's this thing, so we define a type, has some constructors, some parameters in its constructor, and we call this directive spliced with the MK printer metaprogram that takes a term, and it's a tag unit, and the thing will actually generate and bring into scope this function, like a printer for this type, basically, right? Not as the same way as deriving show in Haskell or PPX deriving in OCaml, I think. And but this is actually all done in the user space, right? This metaprogram is completely user-defined. There's nothing special about it. Right. So I briefly glossed over this. So I was saying that in the parsers example, we can get to, since we're kind of scripting over the typing judgment of F-star, we get to make decisions over how to type check certain terms. And this actually is important, since typing in F-star, not typability, but typing, like saying, does this precise term in this precise environment have this precise type, that's undecidable in general. Like a really quick example, it shows that you would need to solve first order logic or higher order logic, actually. so if typing is undecidable, I mean, F star's type checker is only doing its best, right? The actual type checker that F star has is doing the best it can, but it's not necessarily doing it's not going to type check all programs. And if you know of a new way to type check a program, but you don't want to go and modify the type checker in F star, you can actually use meta F star to generate the typing derivation for it in whatever way you see fit. Yeah, that was about it.
So all types that are checked that way are valid. In other words, you can't actually write a bad tactic that would, type check an incorrectly typed term.
So in practice, I guess the engine might be wrong, and you could. But if you follow the typing judgment, then no. So it's you can know that you apply the rules safely. Like each obligation, you can see that it's safe. But actually deciding, is there a derivation that ends with, say, this one? That's unsaidable. You do not know where to look for it, right? It's like, this actually is equivalent to proving.
Sure, yeah.
Oh.
Yeah.
So if you trust the primitives
Yeah,
that are in the TAC effect,
yeah,
and each of these primitives, you can see them as like inverting a typing rule of F star.
okay, right.
So if you believe that we have correctly exposed the typing rules of F star in these handful of primitives, then you cannot construct an invalid typing derivation using the tactic.
Okay, so okay, you can construct arbitrary new terms, though, right?
Yes.
Yes.
You can build a piece of syntax, and it's
Yeah.
just syntax. It's just data.
Yeah.
And if you want to say, hey, use this piece of syntax as a term of type T,
Yeah.
at that point you have to show that you
I
build
see,
a
okay,
valid
okay.
derivation for it.
Okay,
Right.
you can't fool into the thinking that it has
So
a wrong
you
type.
cannot override and you cannot have conflict, basically.
Yeah.
With that's what you're saying?
Yeah.
Is it like-
Yeah.
And that's also why you don't have non-determinism, perhaps. What if you have two different things that we try one way and you come up with type 1
Uh-huh.
and the other type 2, for instance, and both go through? You do not have confluence anymore. You don't have unicity anymore.
Yeah.
What if you have, say, always try this one first? Well, if you succeed with this one, you stop,
Yes,
right?
sure, yeah.
I don't know.
Yeah, okay, yeah, that's one way to see it.
Mhm. Okay. Okay. Sure. So this was kind of showing how we can actually use meta F star. You can actually see it as a way to script F star's typing judgment to do whatever you want. But we actually went a bit further and started to type check the way the tool itself works. So in Surface F star, in the thing programmers use, there are implicit arguments, as in pretty much every proof assistant ever, which really have no semantic meaning, right? But they're extremely useful. So they're usually solved by higher order unification. Just when an argument has to be a certain term, then it gets solved to that term, and otherwise it's just unsolved. But sometimes you might want to define your own arbitrary strategies for it. So we actually provide, so the hash is the syntax for implicit arguments in F star. If this was like this, then Y would be an implicit. That would never be solved because there's nothing to tell what Y is supposed to be from the types. But by adding this is a tactic. This is tactic, which is actually depending on the previous argument X. And this is saying, if this syntax is saying that if Y remains unsolved, then call this tactic to see if you can find a term for it. And this actually just tries to use X. So essentially, this defines a default argument for the second argument of this diagonal function. So if you just write diag 42, you're going to get this, because it's going to get, you have a free implicit here, and we're going to call the tactic to get it. But if you give it explicitly, then you get a different thing, right? So it's a way to give default
You
argument.
said if it remains unsolved, so I guess I would think that you might instruct it to try the tactic first, because I know it's going to work. Why waste the time?
I guess, yes. So why we actually made that choice, I guess, is to allow for this, to override it. Although I guess in this case, it wouldn't actually have an implicit to solve. Yeah, we could think about it.
Heads up on time.
Oh, okay. How many? Oh, wow. Okay.
You started at like 7 classes.
Okay, yeah, let's blast through this. I'm like halfway through the slides. So, another thing you can do with implicits, not important. This is the important one. Once we have the, so we have two cool ingredients: generating top-level definitions and solving implicit arguments. So type classes are like shouting at us that we need to implement them, and we define. This is actually everything I'm going to show you is absolutely user space. There's no compiler support except when I say there is. So we have a module called f-star typeclasses that has an MK class and TC resolve tactics. And then what we can do is, in any other module, you define a type like this, and it has an equality and a proof that the equality is actually correct. So a decidable equality and a proof that it's correct. And we call splice of MK class, giving it the name of this thing or a quote. I'm not sure which one it is. And this will actually generate these two definitions that are polymorphic in the type, sure, and just project from this type the function and the proof, each of the fields. But the field, the record argument, it's marked with this TC resolve tactic, so you do not need to give it. And it's going to run TC resolve to instantiate it. So now you have EQ and EQ OK that are overloaded and are going to run TC resolve to try to find a dictionary for it. And since we don't want to write all this crap, we just give some sugar for it. This is actually compiler support, but that's about it. Class just does, the word class just does all this. It's like no EQ type and then puts the splice. That's it. And we also have this syntax for TC resolve arguments. This basically means it's an implicit for TC resolve, and that's it. And then we have instances, which are just definitions of this type marked with this attribute. Attributes are an f-star thing that you can put in every definition. We also give sugar for this. Instead of writing this, just write instance, yeah, and that's it. You can also define parametric instances and whatever, and superclasses. And TC resolve, the thing that does the resolution for dictionaries, is actually this. It's like 20 lines or something. The MK class is actually a lot larger. And this is basically a backtracking search. Where do you see it? It's in use in the ORLs here. ORLs, and first, all of these are combinators that allow you to do some backtracking. And as soon as something fails and you go back, the proof state is reset, along with all unification meta variables. So you're like completely clean in the point where you started. And the only thing this does is try all the local. So you have a goal for a dictionary, try all the local binders, and then try all the global ones. And when one matches, you get arguments to solve, possibly. If your instance is like one of these, you get a new one. Just recursively go through them. And this is like a quick implementation of type classes, which works pretty well in practice, I think. Besides solving implicit arguments, another thing we do, so f-star code usually extracts into OCaml, and that's where we compile and run it, or it extracts into C as well. And sometimes, and you're going to hear about it, I think, in the next talk, you have shapes of, you have equivalent shapes of a program, semantically equivalent, but one of them more amenable for verification, and one of them that you actually want to run because it's faster. So you might want to, just before extracting, try to modify it in some way via metaprogram, doing whatever you want. And the trick here is that the metaprogram, this thing will ask you to prove a goal of your old definition equals something new. And you need to instantiate and both instantiate and prove that things are equal in order for a star to accept this. So you can only rewrite things into equals to try to keep it safe, right? Otherwise you would just do whatever. So with this like small code, during verification, this tactic generates a huge number of additions. This is a toy example, of course. And in extracted code, you just get the result because this is calling compute. The equality is enforced because the goal is an equality. And meta-star checks that it's actually proven. Right, so you tell me if you want me to skip anything.
I think.
How long do you have the room for?
So I think
Until 3, I
see
think.
this, like we have 45 minutes for 2 talks, and we're getting lots of questions in line. So that means you won't have questions at the end, but you can go until I'd say does it take another 8 minutes?
Yeah.
Is that
Okay.
doable?
Sure. I think it's doable. Sure. So another benefit of defining the metaprogramming effect just as a new effect in F star, using the standard mechanism and all that, is that we can actually extract them into OCaml code as any other user-defined effect. So by default, metaprograms are evaluated in the normalizer, like the abstract machine that performs beta reductions and all that. Inside F star, it's interpreted. And the primitives call into compiler internals and come back with a term, right? And there's a translation in the way. As an alternative, we can actually just extract the things and link them back into the compiler. So a quick view is the usual lifetime of an F star program is you have hello world FST, F star makes it into a OCaml, and you compile it into an executable and you run it. And F star itself is actually written, like the F star compiler itself is actually written in F star and follows this same path. And now if you have a file with a tactic, this new support allows you to you extract the tactic with F star as well, and you compile it, but you compile it into a dynamic object. And then you use a flag to load it into F star and basically gaining a new primitive step, such as, I don't know, like addition is a primitive step that implements the addition of integers. Now you get a new primitive step for the tactic you just defined. And it hooks into the normalizer and whatever, but you get huge speed gains, both because it's no longer interpreted, and also the barrier between interpreted and the actual source code is gone, and now they work on the same data structures. Forget about this example. So coming back actually to the type class example, this TC resolve tactic is marked with this attribute that allows you to compile it, to extract it to native OCaml code, compile it, and load it into F star, and you get type class resolution, which is what's a user metaprogram. It had no primitive semantics, no trust assumptions, nothing, to be added back as an F star extension. And there's nothing that it can do that to make F star go wrong, right? There's no need to trust it. And there's significant efficiency gains. On some examples, we see it running, I don't know, 15 times faster. And that's just one example, right? Anything you think of, you can define a metaprogram, compile it, link it back, and you extend F star by defining a metaprogram in F star. So that's why the title was kind of extending F star and F star. No addition to the TCV, of course. This was just completely trusted. Right, I'm pretty much close to done. So now there's many use cases that people have been developing over the past year, I guess. But here's one we're kind of working on in verifying concurrent programs and using concurrent separation logic inside F star. So this is following work that Asim and Monel did in MSR Bangalore, and maybe UNIC as well worked a lot on this. So possibly the hardest part about verifying concurrent programs is worrying about resources and ownership and how the different threads interact. And actually, worrying about resources, it's already a problem in single-threaded programs to do verification efficiently. So separation logic was invented in the, I don't know, 70s, earlier maybe, I don't know, to have more compact ways of specifying and verifying effective programs. Yeah.
Concurrency, so you assume that the concurrent programs are deterministic, or you have to prove that they are deterministic first, sort of, or by construction?
In the current formalization, which is relatively new, so it might change, they are deterministic because they're completely separate. So there's no, they're not racy. They do not, if you want to read a variable, you need to exclusively own it, and no one could write to it. So there shouldn't be any.
So you kind of join fork kind of things, or by construction, you check our data flow style kind of concurrency. There's no race, no locking.
There's locking.
You can have deadlocks then. Kind of.
Yes, it's a partial
So now you
correctness.
have determination. Is partial correctness that you're talking about?
No,
here?
we're talking about partial correctness of concurrent programs.
Okay.
Mm-hmm.
Thank you.
Yeah. Right, and so separation logic by itself, even without the concurrency, it's already challenging to get into F star because of the solving for heap frames had pretty much every primitive or every combination of steps that you need to do. And by some careful design of the specifications for the primitives and the effect of the state, we can make them like evident in the verification conditions and design a tactic that will find them and instantiate them appropriately, and use the tactic to solve for all of the heap frames before calling the SMT solver. While calling the SMT solver to try to find the frames, then just forget it. It's just not going to happen. But by doing this, the size of the tactic is not so great. It's just finding the heap frames, instantiating them, and descending, and trying to leave everything as it was, except for instantiating the heap frames, and then calling the SMT solver. And that works decently well. So I'm not going to go into this, I guess. There's the specs for the actions, and they have like the footprints and how they change the heaps, and they need to be in kind of in a particular shape. You cannot just write any kind of predicate, so the tactic can find it. And what basically happens is when you get a verification condition of this style, where this is the frame, this is like the frame rule, and you get a left heap and a right heap, and you need to show that your current heap is the combination of both. And well, the tactic finds these things, uses the canonicalizer from before actually to get these things in the same shape and find the frame efficiently, or to find the frame actually, instantiates and then sends most things to the SMT and then heads on into the continuation to get the rest of the things. For concurrency, we're adding some more operations with some more intricate specs and locks. I mean, so that the main additions are parallel composition of two programs and locks working over some footprint and keeping an invariant of the resources that are locked. And here's a tiny example that shows. So we allocate two references and make a lock with the invariant that they're equal, and then make a parallel composition of this that will acquire the lock, increase both of them, release it, and all of this verifies by checking that the invariant holds at any time you release the lock, and you get to assume it at any time you acquire the lock, and all that. So those are the baby steps we're taking in concurrency for now, I guess. So I think I'm getting done. The next steps that I see for this in the short future, I guess, are actually to make usage of meta abstract tactics more widespread. It seems to be something that we're using. We're relatively few people using it. Well, it should be more of a standard tool that you use. Efficiency is it's usually concerned when you're working with very large things you need to prove. For example, the separation logic. It tends to take a lot of time to even run the tactics. Then, yeah, and just like nitpicking improvements over the thing, and that's about it. So I'll take any questions you have if you want, and thanks for listening.
Some questions, if any, as Zoe sets up?
Great.
So what do you mean by bug extermination? I couldn't hear if you talked about that.
No. So I skipped over these three. I just mean that there's some bugs in many places that we need to fix. It's scattered all over places.
So, in terms of usage, is there a notion that is this still in flux, or has it kind of settled? At what point do people take a dependence on it, assuming that it's going to stay the same?
Right. I don't know. I think it's relatively stable. It's I guess you're.
Did you have to make changes when you went to the concurrency? Did you have to make changes?
Not to the engine.
Okay.
Well, or possibly fixes in the engine, but no real changes. Yeah, so it's been pretty much over a year that it's existed, and I think writing a metaprogram is relatively stable. Yeah, I think it's relatively stable.
So in terms of the type class primitive, is that a primitive that could be used to construct, obviously it's used in Haskell, right? And so at some level, I'm just wondering, if now you have it as a mechanism, would structuring F-star programs around it be useful, or is it just sort of a side thing?
I think it is, but it forces you to take a dependent. So the, tactics are also, I think you need this, right? Meta itself is also like, in a way, pretty user-defined. So it's in a module, and it has a bunch of dependencies. So if you wanted to define, say, the addition operation, which is like in the very most basic F-star module, it forces you to, in every program, to load the tactics module and all of its dependencies. So it's not so clear that you want to do it right away.
I see.
But besides that, I think it should be usable everywhere. So yes.
I think it's also a question of, we haven't had type classes for a while, so people have found creative ways
Just
of,
different ways to
of,
get,
of
yeah.
doing it, and now it's like, here you go, here's this new technology. Do you want to change all your existing code?
No,
to this?
yeah, that's
Right.
always
So
Yeah.
there's that.
I was just curious if there was sort of a belief that there were opportunities now that you have them in terms of restructuring.
Yeah, I think there are some, for sure.
Hi all, thank you for being here. And thank you, Jonathan, for the introduction. So verification of stateful programs is essential when it comes to scaling verification to real-world applications. Many of these programs are low-level code that is written with efficiency in mind, and this is often not amenable to formal verification since it involves explicit reasoning about the state and properties such as liveness, memory safety, that is making sure that a pointer will not be used if it points to null, and aliasing and things like that. So over the years, a lot of program logics have been developed, including HOR logic, separation logic, weakest precondition calculus, and things like that. And of course, that gave rise to tools that implements these logics. And some of them are Pharmacy, Daphne, VST, and of course F-star, which I'm going to be focusing for the rest of the talk. So a very brief introduction in F-star. So most of these things have already been covered by Guido. So at its very core, F-star is a purely functional lambda calculus language with dependent types that allows formal reasoning by, as usual, treating proposition as types and proofs of these propositions as programs with this type. In addition, in order to facilitate reasoning about stateful code, F-star has an extensible effect system that allows monadic encapsulation of effectful programs. For instance, we can have ML-like references by writing a program in the ST effect, and that we can have references and we can treat them as ML references. And in addition, F-star is equipped with a weakest precondition calculus that allows us to prove things about these effectful programs. For example, for this function here, incur, which was also Guido's example, and we haven't talked about that. So we can prove that if L is a pointer defined in the initial heap, then the value of L in the resulting heap will be 1 plus the value of L in the final heap. And the way we prove it is F-star will infer a weakest precondition for this program, and then it will ask the SMT solver if the weakest precondition, if the precondition of this program is stronger than the weakest precondition inferred for this particular postcondition, and then we are able to prove that this postcondition is true. One of the recent advances in F-star is low-star. So low-star is a subset of F-star that enjoys a translation to C. So if you wish, it's a shallowly embedded subset of C in F-star. And it comes with a compiler, namely Kremlin, that allows us to extract F-star code to C and eventually run it. So Lowstar provides access to a ComSer-like memory model with the stack and ST effects, and allows us to write efficient low-level code with full verification power of F-star. For instance, we can write this program swap that takes as parameters to pointers and then swaps the values of these two pointers. And we can, again, annotate the resulting type with pre and post conditions. And the type of pre and post conditions reflect the C memory into the logic. And this is the reflected memory, the type of reflected memory. So the specification of this program says that if P1 is live in memory and P2 is live in memory, then the values of these two pointers will be swapped after we run the program. And Lowstar has been successfully used to verify many crypto implementations and has been used to build a library of crypto primitives, namely Hacklestar. And
so every Lowstar program is a valid F-star program.
Yes.
And I only notice if I use too much F-star once I run Kremlin, right? Because it will fail. It will say, oh,
yes.
Back, you have a closure there. There's
Right,
no
that's
like
right.
straightforward translation of closures to C,
Mhm.
so no.
Right. So usually you develop like in F-star, and then every once in a while you run Kremlin, or is it?
Yeah, roughly after a while you get a sense of what works and what doesn't. So by the end, it's only a couple of minutes left to fix.
So, and in Lowstar, I can do anything that's just about proofs. I can use the full power of F-star.
That's correct.
Yes.
Including tactics.
Yes.
Oh, we most definitely use tactics, and we've started heavily using them to metaprogram low-level code so that we don't copy paste.
So here is an example of a very common style in Lowstar. So assume that we want to write an implementation of AES encryption algorithm. So this is how the program would look like. So we have a few parameters. We have the key, we have the initial vector, we have the input, which is the ciphertext, and we have the buffer where the program will write we have the input, which is the plaintext, and we have the output, which is the buffer, where the program will write the encrypted plaintext, that is the ciphertext. So we have to require that all of these buffers will be live in memory, and we also have to make sure that there is no aliasing happening in the arguments of this program. Then we ensure that the parameters will be live in the final memory. I meant to write M prime here. I'm sorry, that's a typo. And finally, we can prove that the result of this implementation is indeed the AES encryption algorithm. So, as you can imagine, the interesting part of this proof is here, where all of the rest is boilerplate that is associated with the generality of the memory model we have access to. Since we have access to the full C, ComSer-like C memory model, we have to be very explicit about liveness of pointers and avoiding aliasing.
And I guess you're not even showing all of the boilerplate, right?
Yes,
I mean,
I'm
the
hiding.
fact that it's only modifying, the output
Yes.
buffer and more pairwise stuff in the precondition. So
I'm even hiding parameters here.
yeah.
It's a very pseudocode style. So to alleviate some of the proof, some of the boilerplate in this proof, what is common to do is to provide a high-level implementation of the encryption scheme. And this high-level implementation, instead of having access to the full C memory model, will only have access to very customized memory model where liveness, one does not have to reason about liveness, and in addition, we can control the amount of aliasing that is going on. And in particular here, there is no aliasing in this record. So this is the state that's particularly tailored for the IS algorithm. And we have 4 fields, which is the key, the initial vector, the plain text, and the ciphertext. And these are all represented as sequences. This is a pure data structure. And then we can write, provide a high-level implementation of IS algorithm that is much lighter in the specification. Particularly, the precondition is trivial, and then we have that it implements the IS algorithm. The result of this implementation implements the IS algorithm, and then. What we can do is to prove that our low-level implementation refines the high-level implementation. So in particular, the specification of the low-level code will be as boilerplate as it was before, but here, instead of having the actual thing that we want to prove about this implementation, it will have it will ensure that the low level implements the high level code, which in turn is proved correct with respect to the specification. And this kind of is a separation of concerns. We have the high level proof, that is the essence of what we want to prove, that captures the algorithmic properties of our program. And we have the refinement proof, the proof that says that the low level refines the high level, where we can hide all of our boilerplate and all of the reasoning that is required by the general memory model that we have access to. So the question that we are trying to answer in this work is how much of the boilerplate code and proof can be generated automatically. Or if you wish, we are trying to systematically approach this style in order to find out patterns that will allow us to make it more automatic. So let's start by observing the high-level computations. So high-level implementations are purely functional programs. They do not have side effects, and they are written in monadic style, so that the state threading is implicit, and we can write them in a convenient way. So let's start by defining the type of high computations that we are interested in. So it's basically a state monad, where the state is a high-level state that denotes the view of the C memory that we are interested in, that the high-level programs operate on. And the only this is a vanilla state monad, with the only difference that is also indexed by a weakest precondition that allows us to reason about the behavior of the program. So basically, if a high-level program has this type, it means that for any initial state and that for any postcondition, if the inferred weakest precondition holds, then we can run the program, and the result that we are getting out, which is the result and the final state, would satisfy the postcondition. And we provide a DSL for high computations, which is a monadic DSL. It has return, bind, get, and put, the actions. And in addition, recursor, a combinator that allows us to write for loops in a very imperative-looking style, but not imperative. And F star allows us to extend the effect system and declare this as an effect, which is very convenient because, of course, we can write programs like that using a bind and return explicitly. But after we define the high effect in F star, we can turn our high-level programs into this. This program that looks smaller and more elegant.
Sorry. So
Yes?
if I understand correctly, so your DSL has a formal semantics that is defined in F star,
Yes, pretty much.
but it's not a subset of F star.
It is, yes, it is.
It is a subset of F
Uh-huh.
star, directly.
Yes.
Construction, you have formal semantics. No?
Yes, yes, yes.
So when you call DSL, not a subset of F star,
It is an embedded DSL.
is it what?
An embedded
What does
DSL.
that mean, embedded?
It's shallowly embedded into F star.
Is what?
Shallowly embedded into F star. It's
Shallow, what? Shallowly, yes, what does that mean? What is that?
it means that we basically the combinators of our DSL are themselves F star programs.
Okay, sorry. It means you just limit yourself to calling
Mhm.
the 5 functions that you see on the top, and we call that our DSL.
It's a library, but it feels like you.
It's not a language,
Yes.
it's a language, right? A language.
Libraries
no,
are
no,
sometimes
no,
languages. I
it
mean,
doesn't
you know,
exist.
APIs are
Yeah.
languages. I mean,
It's also philosophical.
Yes, exactly. This is a philosophical question.
Simplify, please.
there's a
As
long
few
tradition.
fancy word as possible.
Maybe, but
Shallowly, I learned that one, thanks.
We can.
Hey, we like to put Greek letters and feel very smart about ourselves, so that, it's valid for the
I
words
got that
we
part a
use.
long time ago. Thank you.
This is not true when you're in Greece, though.
I mean, this phrase, this terminology, embedded DSL is a very, very
No, I
familiar.
apologize, I really truly now understand exactly. No problem. It's a joke between us. Talking about it.
But I love embedded DSLs, and I think in the end, right, it is just a library, but usually has specific attributes, like they are closed, like all the components you use, they end up being the same domain all the time. So you're like in your own language then. I mean,
It's a library that is domain specific.
And it's all libraries are specific. Anyway.
So here is the running example for this framework. We can write a program that reads 2 locations and then moves the contents of the first location into the second one, and the sum of the 2 locations into the first one. This is inspired by writing a program that computes the nth Fibonacci. Basically, it's the procedure that would be run by the for loop in this program. So it's not entirely artificial, just slightly artificial. So the program will read the 0th location of the state, of the high-level state. We read the first location of the state, and then we'll put the sum at the 0th location and the 0th contents to the first location. And we can write a WP saying that captures the semantics of this program. And the type of this program will be a high computation with unit type, sorry, that's a typo, and this particular WP. Let's now try to study how we can take high-level programs and map them into low-level programs that operate on the full C memory model. So first of all, we need a low state, which we denote L state, and it is the pointers to the C memory that correspond to the high-level view that we are manipulating in our high-level code. And this and it comes with 2 functions. First, that is a pair of lenses that allows us to go back and forth between the low-level and the high-level states. So we have the up arrow that takes a pair of memory in the low state and gives us a high state, and then that intuitively takes low-level state and turns it into high-level state. And then we have the down arrow that takes a pair of memory and null state and a new high-level state, and it applies the high-level state to the low-level state in order to obtain the new low-level state. And we require that these two functions have three properties. That is, if we start by hiring a low-level state and then we lower it again, we get exactly the same memory. If we lower two times successively high-level state, then only the second lowering matters. And if we hire a low-level state that we have obtained by lowering a high-level state, we'll get again the exact same high-level state. So let's see how low computations look like. So low computations are programs indexed by a weakest precondition of a high computation and a high computation that defines what is going to be the behavior of the low-level program. So they are parameterized by the low state, and they are computations in the ST effect of low star. So their specification is saying that if we start by a low state that's well-formed in memory, and if the weakest precondition of the high computation is satisfiable in the high state that we obtain by hiring the low state, then the resulting the low state will be well formed in the resulting memory. And if we run the computation in the state we obtain again by hiring the low level state, what we will get a result that will be exactly the same result as we get by running the low computation. And the memory will be exactly this, the resulting memory of the low computation will be the same as if we had applied the resulting state of the high computation to the initial low-level memory. This is a bit elaborate, so please interrupt me if you have questions.
So why sometimes is lowercase the first arguments of the arrow?
What is that?
Is lower sometimes is
this is
The second one is a type.
the second one is a sorry.
no, because the previous slide it showed up one time.
Yes.
I thought that there was some meaning there.
So the up arrow has only one parameter that is a pair of memory and low state, and the down arrow has two parameters: the initial pair of low level memory and state, and the high level state that we want to apply to the low level memory.
The down is the put, so that it has the old initial state, then the new and the new value you're trying to put, and it gives you back the new initial state.
Why is an updated high level state?
Exactly.
To the low level state.
Yeah.
So really what we're trying to do here is by construction relate low-level stateful programs to their high-level pure counterparts, so that instead of writing the low-level code first and then fighting to show that it does the high-level thing at every step, at every combinator, the two are constantly related.
Mm-hmm. And again, low computations come with DSL. That's very similar to the high-level DSL. So the only difference is the type, which is now indexed by the weakest precondition and the high computation as well. So we see that every low-level combinator is indexed by the corresponding high-level combinator. So I'll return refines return, I'll bind refines bind, get refines get, and so on and so forth. And we can write shift and sum in this low-level code style. So this is what we've seen before, and this is the corresponding low-level code. So now, instead of having just a pair of integers for the state, we have two pointers. Instead of using the high-level combinators, we use the low-level combinators, but the shape of the program is exactly the same. And we know by the type that the low shift and sum program refines the high shift and sum program.
And so the refinement relation that you define this way is fixed. That's correct. And so now, whenever these steps, it forces every step to match when a step is complete. But the user, like if you want to do a performance optimization in the low-level one, you could add intermediate steps where you might break, for instance, the equality of values. But when it returns, then you have to force them to return the same value. Is that correct?
Yes, but the general idea is that the whole high-level program will already have the handwritten performance optimizations, and the only difference between the two programs will be their access, their memory behavior.
I see.
So we want to separate reasoning about the algorithmic behavior to reasoning about the memory behavior.
Welcome to reason on the high-level program later on to show that it's equivalent to an even simpler high-level program.
So the question is, how can we write the high computation? We only want to write the high sum and swap program and somehow obtain the low sum and swap program. And we know by virtue of typing that it will have the correct behavior, but we don't know yet how we can obtain automatically. And here is a very simple and straightforward way to obtain a low computation from a high computation. So we can write a morphism from high computation to low computation as follows. So assume that we have a high computation indexed by weakest precondition, then we can trivially turn this into a low computation by saying, get the current memory state, F star allows us to do that, and then turn it to a high-level state and run the computation C. Get the result, and then update the current memory with what we got as a result from the high-level computation, and also return the result of the computation. And that will give us a low computation that has exactly the semantics that we want, but however, it doesn't have the memory performance that we want, because it doesn't, in fact, operate on the memory, it operates on its own memory model, and then we just apply the differences to the memory, to the current memory. So this is not yet exactly what we want, but it's a very good step towards that. So we know that shift and sum low and morph shift and sum, the low-level program that we obtain trivial, have exactly the same observable behavior. So the first question is, how do we formalize that? We have two low-level computations, and they have side effects, so we cannot run them into the logic. So how we can define this as a predicate over low computations? And second, how can rewrite morphism laws? And I will show you very soon what are the morphism laws that this function, that this morphism satisfies. How can we rewrite? How can we apply successive rewrites of morphism law equalities to obtain the low-level version, the desired low-level version of the program from the trivial low-level version of the program? So let's start by trying to define equality of low-level computations.
So I might suggest you go a little quickly over this part.
Okay, so I will present this very intuitively. This is the type of weakest preconditions for low-level programs, and we define that two low-level programs are equal if their weakest preconditions are precise. That is, they capture this, they precisely capture the behavior of the program.
You want to rule out the generate
Yes.
weakest preconditions that would tell you nothing. Like you you want to rule out something like true, it doesn't tell you anything informative about what happens to your arguments.
Mm-hmm. And then we require that these two weakest preconditions are precise, and also that they are equisatisfiable. For every initial state and every post condition, the first one is true exactly when the second one is true. Then we define low equality as equality of the low weakest preconditions, and then we extend our assumptions with an axiom that says that if we have LEQ for two low-level computations, then we have equality for two low-level computations. And using that, we can prove these nice equality lemmas that says that applying morphisms to the high-level combinator gives us a low-level combinator. Applying morphisms to bind is the same as lbind and pushing morph inside. And morph of get is lget, morph of put is lput, and morph of for again pushes morph inside. And here's the high-level picture. We have a high-level computation that we can turn with morph into a low-level computation, and then we can successively apply the rewrite steps in order to obtain the low-level implementation of the program, which is exactly what we want it to be. And our goal, and what Guido has already started working on, is to be able to use transformations with a tactic, and we aim to build a generic user-defined equality-based program transformation framework that will be able to rewrite with equalities, proven correct in F* and provided by the user, in order to perform optimizations on F* programs. Here is the final picture and our goal for this work. We want the programmer to be able to write the high-level implementation of encryption algorithms, and we aim to automatically derive the low-level implementation of the algorithm that is, and the proof that it refines the high-level implementation. And we plan to apply this into implementing more cryptographic primitives and extending the already existing libraries for cryptography in low-star. This concludes the first part of the talk. The second part of the talk is just 1.5 slides, though. So I will briefly talk to you about another line of work, another project that I worked on during the first month before the postal deadline. And this is normalization by evaluation in F*. So Guido talked about tactics, and tactics are F* programs executed at type-checking time. This means that they are interpreted and often not as efficient as we would like. So an idea, also followed by other proof assistants such as Coq, is to interpret F* programs in terms of OCaml programs, which is the host language, is the language where the type checker is written. And then use the evaluation mechanism of the host language in order to evaluate these terms, and then translate them back into F* values. And we know that the translation of these OCaml terms into F* AST will be values. This is the property of our evaluator. So NBE looks like that. Translate E in the empty environment. This and then read it back into, this will return an OCaml term, and then read it back into F* AST, and we know that this term will be a value. And then we can, when we write the program, we can insert normalization requests for some sub-expressions, and we can tag them, we can add a flag to notify the normalizer that we want to use NBE for normalization of this sub-expression. And then whenever the normalizer will hit an application node, if the head of the application is a normalization request, and if the flag for MB is on, it will just use the normalizer to normalize the F-star term. And this turns out to be orders of magnitude faster than the interpreted code. And it was part of the POPL 2019 submission. And this concludes what I had to tell you today. Thanks so much for listening. I'm happy to take questions.
But that's the POPL submission. Right.
Yes, it is a list of authors. There's
Only got one page.
it's a miracle there's anyone left on the PC that we're not comparing.
So going back to the high to low transformation, so have a bunch of proofs already written sort of at the low level in F-star for these cryptographic primitives?
Yes.
So yes.
So the idea would be to replace those, basically?
Maybe at least. So the idea is to at least use this framework for future efforts. But maybe some of the existing code can be simplified as well. At least
new stuff coming too, like the post-quantum algorithms. We haven't implemented yet. We have high-level specs for some of them, and we'd prefer greatly to write the verified implementations in this style rather than slogging through the
Yeah, I was just curious, sort of, if there were the before and after, you could sort of look at how much simpler it was.
I think that will definitely be one of our evaluation.
There are some simple enough algorithms that it's not too much of a deal to rewrite them.
To just do it, I see. You wouldn't do it if you didn't have to, but for a paper or for some kind of demonstration.
Even then, the existing ones are so hard to maintain. Like there's, for instance, Polygon 305, which does modular arithmetic in a finite field, and it's such a pain because one, the reasons that Guido showed with those gigantic modulo proofs, but also because the reasoning about the math is interspersed with reasoning about the low-level state, and then you're struggling to perform both at the same time. And if you could just split it out and do some code that just is concerned with low-level stuff and is even generated automatically, and then do all of your modular reasoning on sequences and with all the liveness and modifies clauses set aside, that'd be such an improvement.
Has there been any case of legacy code being converted into a proof, or has it all been from specification forward?
We have not. We have not applied yet to any extensive existing code. So basically, we have small examples right now. What we have is small examples written by hand that are basically in the style of shift and sum that I presented here. That's the largest thing that we have applied the framework to, but there's more to come.
But I'm not sure about the scope of your question. I mean, if you're talking about whether we've used Lodestar to verify existing code,
I mean, it was about the experience, what it would be like if there was a practical example, somebody had done the work going in the other direction to see what the experience feels like.
Yeah, so a lot of our crypto code, so usually we don't try to innovate in finding new ways of implementing existing crypto primitives. We take existing implementations that have been hand optimized in C or assembly, transcribe them into Lodestar, and do the proof there.
And then regenerate them.
And then regenerate them, exactly, yes. Yeah.
There was one more question.
So I just another question about the two kinds of proofs. So if you were to use tactics and replace these older proofs with the new style, would they actually execute faster? I mean, would they be easier to prove?
Oh, you mean with the old style but using tactics?
Yeah, well, doing it at the low level as opposed to the high level with translation.
I think that, has anyone tried that, doing the specification proof at the low level and not doing the layering thing?
If you use tactics to do the low-level proof directly, is that what you're
So I'm comparing low-level proof by hand,
Mhm.
and then a high-level translated to low-level with tactics.
Mhm.
Those two data points. Is like, would one be faster? Would Z3 be faster with the tactics, or would it be a wash?
Oh, I think in terms of proving that you can go, you can take a high-level program and transform it down.
Yeah.
There's almost zero Z3 proof.
Right. Okay. So that would be a win,
Yeah.
especially
Yeah.
since these C3
Yeah.
proofs are already complicated.
Yes, so,
Okay.
so we do expect an improvement in verification
Yeah, so
time
it's
as
both
well.
cleaner
Yes.
and faster.
Thank you so
Great.
much
Yeah, good
for the
result.
remark.
Yeah.
Okay. Thank you again.